We'll discuss initially the process control or flag register instructions with examples, followed by a small program on trap flag. Relating to our today's concept, let us write one small program and execute it. This topic is slightly related with the previous topic. In previous topic, we have discussed two instructions called as pop and push. Pop and push are the stack operations. In case if you wanted to use the stack memory, then we need to use two operations called as push and pop. Right. If you wanted to push something to the stack memory, then we use the push operation like push bx. So bx is pushed to stack. So pop ax, push ax. These are the examples that we have already covered in the previous session. In case if you have any doubts, we can talk privately. Okay. Today I may be using those instructions also, but anyhow, these classes I'll try to keep this class as independent as possible with the previous classes. So the main purpose of learning this concept is to improve the programming skills of 8086 to the advanced level. So while doing any application level programming, we need to use these instructions, flag register instructions a lot. And also the stack operations, whatever we have discussed in the previous class, as well as the flag register instructions that I'm going to discuss now. These two topics are very, very important for advanced 8086 programming. So that is the reason why we are learning this concept. Flag register, you know very well, flag register is a 16-bit register. So all 16 bits I am displayed here. Look at here, this is the 16-bit flag register. This is the higher byte. This is the higher byte and this is the lower byte. Whichever you want to store, you can store the entire 16-bit into the stack, and you can retrieve all entire 16-bit out of the stack. Today's topic, what is the thing that we are going to do is that, you know that for every program instruction, these flag bits are affected. So this is overflow flag, maybe it is 1 or 0, depends upon the current situation of the instruction. While executing our program, in case your program has 20 lines, for every line, the flag register is affected. So this shows the exact status of your program. So for every program, for example, if you're writing a high-level language, C language or Java language, there also the program exists, the line-by-line execution exists, and whenever you are doing line-by-line execution, for every line the flags are affected. But you have never come across the flag register during learning C language or Java language. But here you are learning 8086, it's very important to know how this flag register has to be manipulated in order to control the complete process of the program. So right here it means that today's topic will tell you how to manipulate these bits, in case if you want, if there is a demand according to your application, if you want to manipulate this trap flag. Okay, if it is earlier value of trap flag is 1, if you wanted to make it as 0, if you want to unset it. So through program only we can do it. Okay, overflow flag, direction flag, auxiliary carry, parity, carry flag, any flag bit if you wanted to set either 0 or 1, the following topic is helpful for you. This is what you are going to learn. You are going to learn in this upcoming 30 minutes is to how to set or unset any bit of this entire flag register. Look at here, up to trap flag, overflow, direction, interrupt, trap flag, up to here it is 8-bit. So from sign flag to carry flag, this is 8-bit. This 8-bit is lower byte, this 8-bit is higher byte. These are the instructions that you are going to learn. Push F means you are pushing the 16-bit flag data, 16-bit of information of flag to the stack. Pop F means whatever this topmost 16-bit data that is available in the stack, you are popping it, you are popping out. LAHF, I read it as LAHF, load flag into AH. Here the AH, the meaning of AH is the register name. Load flag into AH. So which part of flag is loaded into AH? AH is just 8-bit register. It's not 16-bit register. But flag is 16-bit register. But what part of flag? Flag has two divisions. I already told you, lower byte and higher byte. Whether lower byte is loaded or higher byte is loaded. Lower byte. Please remember this point. Lower byte is loaded to AH. Okay. So once after lower byte of flag is loaded into AH register, you can manipulate it and you can store back that lower byte of AH back to the flag register. To store back that particular thing, we have ahf, that means store the data of ah to flag register. What is load ahf? Load ahf means load the lower byte of flag to ah register. What store? Store means load ah data to the flag register. Okay, so these instructions are very helpful because you can control the entire program. You can keep the control in your hand if you know these instructions, 4 instructions. We'll see an example. Right. Why pushf, popf, lahf, sahf are used? Okay, I already told you that these 4 instructions are used to control the program by manipulating the flag as in the way you want. User can manipulate the bits and they can have the complete control of the program because for every execution, the flag register changes. Look at here, consider a program has 9 lines of code. Of course, I didn't write any program here, but I'm just imagine a program with nine lines of code. For every line, the flag changes. For an example, if I'm performing addition here, if there exists a carry, then carry flag changes, right? So I hope you got the point. In case subtraction, for every arithmetic operation or for every operation for line by line execution, whether you are doing arithmetic operation or not, the flag values changes. The flag values are affected. Now look at the situation of line 4. In line 4, okay, I want the flag to be stored in stack for one of the important reasons. What is that important reason is that whatever the status of the program that I have at line 4, I want to maintain the same status at line number 8. I repeat, I want the status, whatever the flag status is there at line number 4, I want the same status at line number 8. Okay, I cannot directly go from line 4 to line 8. My intention is to execute sequentially only. So, but even though I want the same status, okay. So what are the status, what are the flag data that I have at line 4? The same flag data should be there at line 8. But it is impossible if you continue a program execution like this. Okay, so you can, every program executes line by line only, but for, whatever the data that you had at line 4 will be obviously changed at line 5, line 6, line 7. At line 8, you will have a data that is never equivalent to line 4. So what we need to do at line 4, whatever the flag data is there, that you need to store in stack. 16-bit flag register data, I repeat, you need to store in the stack. This is the way that you are going to play with your program. Okay, so this way you can store the flag data into the stack. So you commonly, as usually, you execute your program line 5, line 6, line 7. The moment you came to line 8, what is that you want at line 8? You want the status of the flag, how exactly it was at the line 4. So at line 8, what you do is that you just pop F. That means you restore the flag register. That means topmost 16-bit of stack will be popped and kept in flag register. Okay, so at line number 4, how exactly the flag status is there? At line number 8, you can maintain the same status and you can keep on continue this thing. Okay, in lots of applications, these kind of things are helpful. So in routine ways, I mean, at any point of time you wanted to you wanted to have a program sequence that is very much similar to the previous one of the blocks of the same program. You can just imagine some set of instructions here, some set of instructions here. How exactly the status that you wanted to maintain here, how exactly the status was maintained here. If you wanted to do that, then these instructions are highly helpful, right? Pushf, almost this instruction is demonstrated. The 16-bit flag register is pushed into the stack. Just imagine a stack segment. Earlier values are 42, 26 are already available. Now you are doing pushf. Pushf means 16-bit flag register data is kept on the top of the stack. How higher byte goes to the higher address, lower byte goes to the lower address. So this is lower byte of your flag register. This is higher byte of your flag register. This is totally 16-bit flag register. So it is stored in this way. Okay, while popping also the same rules are applicable. So what is happening inside after pushf operation? So before pushf operation, your stack pointer is pointing here. After pushf operation, your stack pointer has to come to, it has to point now to FL. That means now the topmost element is FL. How do your stack pointer comes to here? Okay, so you are moving in bottom up direction. So here you need to decrement your stack pointer by 2. Your stack pointer will be decremented for every push operation. Guys, I'm telling you again, This topic is the topic of pop and push was already completed in the previous session. In case if you don't understand how the stack pointer is decremented by 2 and why it is decremented by 2 and why we are moving from bottom to up, for these reasons you should have already followed my previous class. Otherwise you just have a glance. So for every push operation, because since the new data is pushed, your stack pointer, which is very much similar to top pointer, will come here. Okay, it has to be incremented by 2. Pop f, if you have understood push f, then you should understand pop f. So what pop f does? So the topmost 16-bit data of stack is popped into the flag register. So the topmost 16-bit data is stored back into the 16-bit flag register. How? The higher byte goes to the higher byte, lower byte goes to the lower byte. So in every location, you know that 8-bit of data is stored. So higher byte goes to the higher byte, lower byte goes to the lower byte. Okay, so after popping this information, since it is a reverse operation of push, stack pointer has to now point out to this location. Stack pointer has to be incremented by 2. In case of push, it goes upwards, so the value is decremented. In case of pop, the stack pointer value will be decremented. This is taken care by your computer. Now you are just seeing the internal details only. The other two instructions are LAHF and SAHF. Okay, partly I have already demonstrated while I'm saying LAHF. Load flag. What flag? Flag has two things. Lower byte is higher byte is said. Which one you are loading? Lower byte. Load the lower byte of flag to AH. Loads the flag's lower byte to AH. This is the thing that we are going to do. So this is your flag register. Flag register's lower 8-bit. This is higher 8-bit. This lower byte is stored in AX register. In AX, especially AH. So since we are using AH, so the instruction itself using the word AH here. Okay. So FL is stored here. You might ask me, sir, why lower byte only? Do we have any other instruction like L, AL, F? L, AL, F. AL means auxiliary lower byte. We don't have that kind of instruction because very rarely we manipulate the higher byte of flag, but very often we manipulate the lower byte of flag. That's why a special instruction is created to load your lower byte of flag. There is no instruction that loads higher byte of flag to the register directly. Okay, this is very often or very commonly that lower byte of the flag register is manipulated. That's why LHF is used. Okay, in converse, in case if you wanted to, so why we are storing? After storing lower byte of flag into AH, you can manipulate this value directly inside the program. You can manipulate it, right? If all ones are there, you can make all zeros. You can unset any flag. You can set any flag. You do whatever you wanted to do in this particular AH and store back it into the right place. So how to load? You used LAHF. After manipulating the data, you need to use SAHF. SAHF, that means store AH value back to the flag register. Stores AH to the lower byte of flag register. Okay, lower byte of the flag register. This is your AX register. This is AH. So after manipulating, your value is stored to lower byte of your flag register. This is your flag register. Flag register's lower byte, flag register's higher byte. That's all. Very nice. What you have learned is very simple today. Push F, pop F. LHF, SAHF. What every instruction does was already demonstrated. Now let us see one simple program. Before that, since flag register and manipulating every bit is very important for the programmer during application development process, we have some other instructions, also called as implied instructions. I might have already discussed these instructions. For carry flag, you need not to use any additional instructions. It's very nice instructions are already available. For carry flag, if you wanted to set the carry flag, STC. If you wanted to clear the carry flag, CLC. In the same way, for direction flag, you have set direction flag, clear direction flag. For interrupt flag, set interrupt flag, clear interrupt flag. Okay, you can set or unset these three flag bits like carry flag, direction, and interrupt. CDI. Okay, carry flag, direction, and interrupt flag. You have direct instructions. Okay, you don't have to worry of loading that flag register, pop F, push F, that story is not applicable in case if you wanted to change carry flag or direction flag or interrupt flag, because most often, okay, more often these carry flag, direction flag, interrupt flag values are changed by the programmers very frequently. That's why the direct instructions are given for carry flag, direction flag, and interrupt flag. But for remaining flags, you have to do it of your own. One of the important programs, okay, I would always love to give this program during exams. Okay, in case if I am the person who is going to set your question paper for your exam, definitely will find a question on a program. Write a program, demonstrate how to set or unset trap flag. This will be the direct question that you are going to see for your mid to exam, in case if I am the person who is going to set the paper, because I know the importance of this particular topic. This is the program where you are going to use the instructions that I have demonstrated right now. How to do this program? Okay, how to do this program? Let us see the nature of the flag register. First of all, this is the entire 16-bit. What I wanted to set or unset, listen carefully. Trap flag, it belongs to higher byte. When I wanted to set or unset trap flag, do I want to change the other flag bits or do I want to remain the same values as it is? Very important, when you are changing the trap flag bit, you should not violate the existing values of other bits. They should be like that only. Okay, they should be like that only. For an example, you have 1 1 1 1 1 1 1 1, all ones. Okay, all ones are there. Okay, after unsetting the trap flag, you will see all ones here up to, except the trap flag value will become 0, and remaining there should be all ones. So my point, I think it is very clear that your program has to manipulate only this trap flag, and the rest of the flags it should not manipulate. You have to preserve that data as it is. Otherwise, the entire program will collapse. Okay, right. So now in this program, we are going to set or unset this trap flag. Okay, how to set and how to unset. These two things, these 2 points I am going to demonstrate. So the logic is very simple. First of all, you load this entire flag into the stack. I repeat, load this entire flag register into the stack. From the stack, you please load this entire top of the stack to the register. Once this data is available in the register, I can manipulate this bit. Okay, load in any register like AX. Take AX register and load this entire data. You cannot directly load flag register data into the register. First of all, you need to push the flag register data to the stack. From the stack, you need to load it into the register. When I get the data into the register, I can start manipulating this trap flag. My objective here is to make this trap flag as 1 or 0. It depends upon the decision. I want to set or unset this trap flag. And the trap flag bit belongs to higher byte. Okay, now let's look at the logic. I've given some hints for writing program. First of all, load the 16-bit data to the stack. Okay, and then pop that 16-bit data to 16-bit register like AX or BX. Okay, in the higher byte of register, perform the logic. Why higher byte of register you have to perform the logic? Because the trap flag bit belongs to the higher byte. It belongs to the higher byte. After manipulating, store back the stack and then pop to the flag register. Okay, so after manipulating the trap flag in the register, you store that 16-bit, the entire 16-bit register to the stack, and then store that data back to the flag register by popping from the stack. Okay, when you perform pop operation, topmost 16-bit of stack will be kept in the flag register. Pop F, that's what pop F. Okay, now this is the example. Imagine that 16-bit data is stored in a register called as AX. Okay, if flag data is stored in AX, okay, then I need to manipulate only AH. I repeat, I need to manipulate only AH, but not AL. Okay, but not AL, because trap flag belongs to AH. When I load flag register data to AX, okay, then the trap flag bit is in AH. Okay, in AH, if this is AH, so there is something in AL. I don't mind about AL. That 8-bit information I've not written here. I don't want to show it also. This is AH. In AH, okay, this is the trap flag. This is the trap flag. Okay, I'm getting back to the flag register in case if you have any doubt, look at here. So this is my AH. This is my AH. Okay, so from D8 to D15 I have stored in AH. So the last bit, this is what the trap flag. This will be stored in AL. I don't want to manipulate AL. Okay, I don't talk about AL also. Use your common sense. Just use your common sense. No programming technique or no knowledge of computer science subjects are required to do this. Look at here. This is the AH value. I want to manipulate this one. The existing value of this is 0. I want to set this value. That means I want to make this value as 1. Use your logic to make it as 1, such that the condition is that remaining bits should not be changed. I already told you, I want to change only this bit. This should not change. This should be as it is. This should be as it is. I need to change only this thing. Just think how this can be done. I want to set or unset this particular value. That means this trap. This is the existing bit information, and I don't want to change this information. Okay, I want to change only this value. How to change means use logical operators. The hint is use logical operators. For an example, okay, for an example, look at here. What I do is that I'll keep all. If I want to make this as 1, I repeat, if I want to make this as 1, what I need to do is that I'll take 1 here. I'll take 1 here, and I'll perform an OR operation. If I perform OR operation, what are the remaining values should be? So remaining all values should be 0. Then only this state will be preserved. Okay, so 0 0 0 0 0 0 0 1. You perform OR operation. Okay, you OR with this entire data with 0 1. Okay, this means 4 zeros and 0 0 0 1. OR means you already know that 0 1 OR operation will result in 1, and this will be as it is. So the result will be 1 0 1 1 1 1 0 1. That's it. The trap flag is set. In the same way, you can set the trap flag also. You can set or unset the trap flag as well. Okay. In case if you wanted to make it as 0, then the same logic. Okay. In case if you have 1 here. Okay. If you have 1 here, imagine that if you have 1 here and you wanted to make it as 0, how will you make it? If you want to set, we have used OR operation. If you want to unset, I mean, if you want to unset, that means if you wanted to make trap flag as 0, then you have to make it as AND operation. You please make an AND operation. If it is already 1, if it is ANDed with 1, if it is ANDed with 0, if it is ANDed with 0, then the result will be 0. Okay, but the remaining information should be preserved as it is. So what should be kept here so as to make this information as it is while performing especially AND operation? Okay, all should be 1s. So 1 1 1 1 1 1 1 0. It means 4 1s is F, 3 1s followed by 0 is E in case of hexadecimal. Okay, look at here. While performing AND operation, it is FE. While performing OR operation, it is 0 1 0 1. Okay, you AND with FE, you AND with 0 1. If you want to make your trap flag as 0, then it is FE. If you want to make your trap flag as 1, then OR with 0 1. That's all. Now let's see the program. Let's execute that program. The program is readily available here. Look at the program. This is the data segment. I've taken 2 messages to know whether the trap flag is set or unset. Okay, 2 messages, message 1 and message 2. Okay, I think you know how to initialize a string, and these now things are already demonstrated as part of previous lab sessions. Okay, message 1 and message 2. Message 1 is displayed in case your trap flag is set. Message 2 is displayed in case trap flag is unset. That's all. The data segment ends here, and here the code segment starts. Okay, here the code segment starts. These are the routine steps here. I have just initialized the data segment. These are 4 or 5 lines. Whatever I have written here, 4 or 5 lines are routine steps for every program that you will be writing. These routine steps. The last 2 steps out of these 5 steps, that means these 2 steps are used to initialize the data segment. The data, I'm keeping the address of the data segment to the bx, and I'm initializing that bx value to ds. I think this point cannot be directly written as move ds comma data cannot be written. These points are already demonstrated as part of our regular classes. Now, now the actual points start. What you need to do, the very first thing, you are going to manipulate the trap flag. Where this data is available in flag register. What you have to do? Can you manipulate flag register directly? No. What has to be done? You need to store that flag data into the stack. Who does that one? Push F. Push F. Okay, good. After push F, can you manipulate directly into the stack data? No. Where do you manipulate? In the register. Now what you want to do? You store that topmost 16-bit data to the register, 16-bit register. Okay. So in AX, now data is available. In AX, the data is available. Now trap flag you need to set or unset. In this example, I'm unsetting and operation. And operation means I'm unsetting the value. I'm unsetting the value. What is the argument that is used here? I already demonstrated FE. That means 1 1 1 1 1 1 1 0. If you AND this value with the existing flag register value, okay, all the bits will be as it is except the trap flag will become 0. Except that trap flag becomes 0. And then I wanted to know whether the trap flag is set or not. Set or not. What I do is that just show you what is the logic to know whether the trap flag is set or not means. Look at here. So this is the place where you have done. So in case if this value, if you want to know whether it is the last value is 0 or not, you perform the you rotate this entire value towards right side. We helping with carry flag. RCR, rotate carry right, rotate with carry right side. So this value goes to the carry flag. In the carry flag, you can check whether the carry flag is 0 or not. If carry flag is 0, trap flag is unset. If carry flag is 1, then carry flag is set. You have to perform the rotate operation. Okay, you need to perform the rotate operation. Rotate R AH01. Why we are writing this one? To know whether our trap flag is set or unset. The carry flag will be updated with the last value. The last 0 goes to the carry flag in case if it is unset. If it was 1, that 1 goes to the carry flag. I'm just checking the carry flag, jump on carry. Jump on carry means there exists carry where I'm going down 1. So I'm coming to this particular 3 instructions, down 1. In down 1 in AH, I kept 09. I'm changing the offset to message 2. In the message 2, I'll say that since I made the trap flag as 0, this message will be displayed. Trap flag is unset. Otherwise, in case if trap flag is not set, jump on carry will not be 1. If there exists a carry, then you will come here. If there is a carry, you will come here. Jump on carry, you will come to this particular thing. If there exists a carry, what does it mean? Trap flag is set. Trap flag is set, message 1 will be printed. Okay. If trap flag is 0, then carry is 0, then you will come to this particular direction. So whether I wanted to set or unset the flag is all depends upon the value that you are providing here. Actually, my intention is to unset the value because 111 1110 will unset the value. Good. So in the same way, you'll come to down to, I mean, in case if there is any failure with this condition, obviously you'll come to down to. In the down to, since you have rotated towards right side, you have manipulated that AH value. You please rotate back to AH value back, and then you'll get the result back. So here, look at here, the register AX is used, but the same AH I've used for 09 also. Okay, you can change the register here. I'll change this register, it's better. I'll change, let me keep the data in BX so that I'll be manipulating BH every time. So here also BH. I hope why I'm writing these things you should have understood, because AH is being used for interrupt purpose. Okay, BH. Anywhere else or CR. Now let's execute this one. I want to make the trap flag as 0 because the value that I have passed is FE. FE means I wanted to unset. I wanted to unset that particular. I wanted to make the trap flag as 0. So you have executed the program. We have executed the program correctly. Whatever we have written steps are exactly correct, and we have unset the trap flag. Okay. So in the emulator, you can check the flags also, but here the trap flag is not available. That's why a separate trap flag. What is the purpose of setting or unsetting trap flag? I hope you know this flag register is already discussed in the classroom. Trap flag is used for line by line execution. In case if trap flag is 1, the program is executed line by line. If trap flag is 0, then there is no line by line execution. We are executing the program all at a time, all instructions at a time. Anyhow, how to set trap flag, set or how to set or unset, this is a program. In the same way, during your exam, maybe for direction flag or maybe for parity flag or carry flag or whatever the flag it is may be given. So the same approach has to be followed. Conclusion is very simple. I have discussed 4 instructions: pushf, popf, LASX, and SAHF, and I have discussed a program. This program requires the knowledge of pushf, popf, and rotate with carry left and rotate with carry right. I've used simple logics. In order to unset, we use AND operation FE, and in order to set the value of trap flag, we need to use OR operation with 0 1. Okay, if I change this argument to 0 1, and if I make this as OR, OR operation. Okay, if I execute, I hope output should be set. Okay, the trap flag is set. You can see the trap flag is set. Okay, that's all for today. Any doubts? I'll just check it out. Any doubts, you please check, you please send me.